So today I just kind of want to talk about what's new in NX manufacturing. We're going to touch on both the additive side as well as the CAM side, so the machining side. And the idea behind this discussion here is Siemens is now at a point where they're releasing major updates every 6 months. And a lot of customers are kind of debating, is it worth the effort to upgrade all of the time? Sometimes it is, sometimes it's not. And really what I want to do with this presentation is just touch on some of the functionality, especially for any of the manufacturing shops out there, that might make a significant business impact for your operations that are enabled by moving towards some of the later versions of NX. So a little bit about myself. I'm part of the pre-sales team, kind of, as I mentioned earlier, CAD, CAM, and additive manufacturing. Spend most of my time in the CAM and the additive manufacturing side. Before joining Maya, I spent a number of years in the aerospace world, working specifically in consumable toolings for gas turbine engines. So, quick overview of the agenda for today, what I wanted to discuss. On the additive side, I really want to talk about some of the new functionality around print marks. What we see with additive manufacturing is that it's only really being used, at least on the metal side, in what I would consider to be highly regulated industries, right? So they're going to be the aerospace and defense guys, they're going to be the military, they're going to be medical, and the reality behind those industries is that traceability is king, right? If you don't know the history of the part, you may as well not have made the thing. So just, how do we streamline that? How do we work around it? For the second part of this talk, I just want to talk about some CAM operations, specifically around milling, some of the new tool paths that are available, 2306 and moving forward. And we're going to wrap up with a quick Q&A at the end. So when it comes to additive manufacturing, really the one thing that I want everybody to walk away with is an understanding that Siemens offers a true end-to-end solution. We could easily spend an hour presentation on each one of these individual topics, right? So something like topology optimization, I'm just going to say that we have it, we can do it based around various objectives. I'm not going to get into it because we're a little bit more limited on time, but really what I want to just talk about here, especially with the digital thread, is that we're able to take that data set and move it across. Everything stays linked, and the advantage to that is when you have a minor design change, you're not having to rework your entire process. On the additive side, we support the four, I'm going to call them major technologies. So your powder bed fusion, your binder jetting, your direct energy deposition, and your FDM. Anything that isn't purely one of those four typically is close enough in terms of a process strategy that we can adapt one of these four core technologies to. So we support not only the full end-to-end workflow, but we also support all the major additive methods. When it comes to print marks, I think this is something that's kind of interesting. The way that we're handling this now is in the design environment, the designer is going to set the location, the font, everything about that, and just designate. The actual 3D geometry gets created in the additive build tray where we're defining things like our support material. And that's what we see here. So it's actually a feature name. So that makes it very easy for us to automate. It also means that we get that level of traceability, because if this is a PLM controlled file and you want to know, well, what would happen with serial number 22? What machine was it on? What were the other parts on that build tray? We can answer all of that. Here what we're doing is we're just making a very small design change. And instead of having to re-support the full end-to-end workflow, all we're doing is we're just going to jump into our build tray. We're going to update the geometry, and it will automatically recognize that certain areas were lacking support and extend the existing support strategy to those new regions. Most of the industry today around additive still handles a lot with universal file formats, whether those are step files, STL, 3MFs, there's a multitude of them. But what ends up happening is that they're not linked. So this is the classic scenario, is the machine shop ends up calling back the additive guy and going, hey, when we tried to clean up that face or clean up a bore, we didn't have enough materials, a little bit too much distortion. Can you add an extra 30 thou on that surface? And sure, you can. But if you're doing everything in an STL-based workflow, you now need to put all of that engineering effort back into re-supporting, re-simulating everything. By being an integrated end-to-end workflow, what we're able to do is, as you saw in that previous example, just migrate that change over and save a lot of time. And really what we're trying to do is we're trying to reduce the amount of time that's spent on what we consider non-value added engineering effort, right? So you've already done the bulk of the work once. You really don't get anything by sort of duplicating those efforts over and over, and customers aren't really willing to pay for more of that effort. Now, as we switch over to the machine shop and the milling side of things, what I want to compare is our cavity milling, which is an older operation type, to the new 3D adaptive roughing. So in this case, I'm using 2306 as my platform. That's what I'm using just to generate these comparisons. So in this case, what I'm going to be doing is, at the top, you see the cycle time improvements. And sure, that is an improvement, but I don't think that just looking at that and going, you save, let's call it 45 seconds or so, on this operation is all that convincing. I think there's a lot more to it, and that's what I want to do a little bit more of a deeper assessment on. So if we're going to talk about machining, we're going to talk about optimization, we're going to talk about comparing operation types, it's important that we're using realistic parameters. So just for full transparency here, what I'm going to do is I'm just going to share the actual parameters that I use for my simulation efforts. So I assumed that the part above, the previous part that I was showing, was made of Inconel 718. We're going to run 200 SFM with a 2.5 thou chip load. These numbers are largely arbitrary, but they fit relatively, midpoint within the recommended parameters from the cutting tool manufacturer. When we talk about how does that translate exactly over to our cutting parameters, so some of them we've already gone over. In terms of engagement, we're going to be using a 3/4 inch axial engagement. This is a 1/2 inch end mill. We're going to be using 15% radial. We are correcting for chip thickness because of our radial engagement is so low. So our programmed feed rate is going to be 3.5 thou, but our actual chip thickness is at 2.5. So how am I going to present the comparison between these two manufacturing strategies? So what we're going to be doing here is just take a little bit of a detour into a third-party tool called NPRO. NPRO is a commercial development from the University of British Columbia. These guys have been doing FEA-based machining simulation for many, many years. And all we're doing is we're just going to be, in this case, comparing toolpaths. NPRO has the ability to also do optimization around different objectives, but just for the sake of this discussion, I really want to compare the older manufacturing strategy with the newer one in NX, no third-party optimization. So one last look at what the two parts are. So it's obviously identical parts, just a different toolpath. So the first graph that I want to look at is, this is cavity milling. So this is the horsepower required to drive the tool over time. The way that NPRO works is it takes your entire toolpath and divides it into about 1 millimeter segments. We find true cutter engagement at each one of those points. We compare that to the material table to understand the torque, power, and feed force required to drive the cutter through the part. What we see here is over time, so it's the x-axis is time, the y-axis is spindle power. So these are instantaneous spindle requirements. This is the older operation strategy. What I want to talk about is the new tool. So yeah, it is a little bit faster, but more than just being a little bit faster, it's a lot more consistent. So the easiest way to think about machining is what we want to be productive, to be profitable. We want to have the highest average power consumption with the most even process we can. Right? Each one of these spikes is what's going to get us in trouble. That's where end mills are going to break. That's where parts are going to move on the table. That is what we're trying to avoid. What we notice is that while the peak forces on the new adaptive strategy are much, much lower in terms of the peaks, because the average is a little bit higher, the cycle time's a little bit shorter. So horsepower is one thing for us to discuss. How does it compare to some of the other parameters that we want to talk about? So let's talk about what happens with chip thickness. So the actual older tool, cavity milling in orange here, didn't do a great job of respecting our 2.5 thou program feed rate. It averaged it pretty well, but again, we had those spikes. So what I'm going to do now is I'm just going to propose that if somebody was making that previous part, with those feed rates and everything else, I would propose that we can actually increase our chip load by about 20%. using the new tool and be at a fairly similar in terms of peak forces, but now start to realize some pretty significant time reduction. So in this case, maybe it's not exact. What I did is I just multiplied our chip thickness by 20%. That's the gray overlay. And now on the x-axis, we see that we're starting to make some significant time savings. When it comes to the manufacturing world, when it comes to machining, time is money. The faster that you can get a part out the door lets you sort of run the same volume with less machines is always going to be a win. Let's talk about bending force. So that's the next big one that we need to talk about. So when we're talking about bending force, what we really want to talk about is what does it take to drive that tool through the cut, right? How much does the axis of the machine need to push the part over? So here again, we're doing that basic comparison. And again, the older cavity mill that's been around many years, there's got to be millions of parts that have successfully been manufactured with it. What I'd like to point out is just how much better the new adaptive strategy is. We almost entirely get rid of those load spikes, and especially when it comes to bending force, that's what tends to break end mills. That's what tends to make parts slip in fixtures, right? So if you ever had a part and then something ends up happening, the vise moves on the table, most of the time that's because of your peak forces. Again, we can talk about, well, what happens if we increase those by 20% that I was proposing a couple slides ago? Well, even with that 20% increase in chip load, which now we're talking about reducing cycle time about 25% from the original operation, we still have a very, very reasonable bending force compared to the original cavity milling operation. This opens up a little bit of a discussion. Because the new operation is so much more stable, do we start talking about going to larger tools, larger depths of cut? How do we gain even more productivity? Because really now our spikes are about a third of what they used to be. So if you were successfully manufacturing parts before, there could be some significant optimization potential here. So key takeaways on this in terms of comparing. So adaptive, 3D adaptive that I presented here is the 2306 version. If you haven't given it a try, I strongly suggest that you consider giving it a try. In terms of the cost reductions and why I think it's important for us to consider, I'd really like to basically look at three aspects of it. And I think that these are in the order that you'll probably recognize them first, right? So the first one is cycle time. You'll immediately recognize that reduction in cycle time, increase in productivity. The next one is by removing those load spikes, we actually expect our tool life to increase. Tool life will increase measured in consumable cost per part. It may be fairly similar in terms of the number of tools you'll go through in a week, but you'll get more parts out of your shop in that week. The last one is going to be spindle and general machine life. Right, so these load spikes is what's difficult on a machine. It's what will ultimately lead to having to rebuild spindles. So the better that we can treat those spindle bearings, the longer it lasts. Another little kind of cost savings for us there. Key assumptions here that I just want to touch on just to kind of highlight them is, especially for that 20% increase in chip thickness, I'm assuming that our process is stable. We're not fighting chatter. And my second assumption is that you're able to actually evacuate that chip. There's enough room in the flute of the end mill, and you've got enough coolant flow. If you're in a deep slot or something, this may not actually work just because of chip evacuation concerns. So with that, it was a little bit on the shorter side, but if we've got time for any questions.